Hello, my name is Selma, and today we will be learning about how to solve a buffer system using a weak acid and a strong base at equivalence point. At equivalence point is when the moles of acid equals the moles of base, and it's important to note that the pH will be higher than 7 because the weak acid will act like a weak base. Both the acid and the base are going to be fully used up at the end. It's also important to know that the ice tables in this reaction will be in moles because the concentration values keeps changing, as well as for the second ice table, the salt will dissociate into ions when put in water. We will be doing an example to explain. A chemist titrated 25 ml of a 0.1 concentration of acetic acid solution, as well as a 0.1 concentration of sodium hydroxide. Determine the pH of the resulting solution when 25 ml of the base has been added. Over here, we have written the equation with acetic acid plus sodium hydroxide equals the salt plus water. Our first step is to calculate the amount of moles of sodium hydroxide as well as acetic acid in 25 ml solution each. Both of the values will be the same, as both of the concentration and the volumes will be the same. Our second step is to put all of the information into an ice table, and over here you could see that at equivalence point, both the acetic acid solution, as well as sodium hydroxide were fully used up, and the salt now has a mole of 2.5 times 10 to the power of negative 3. The third step is to figure out the concentration of the salt, so we divide moles per volume, and equals 0.05 moles per volume. And it's also really important to know that the salt eventually becomes the acetate ion, because sodium is a spectator ion, and the acetate ion now reacts with the water to produce hydroxide ions. Over here at the equilibrium expression, we can see that the acetate plus water equals the acetic acid plus hydroxide. The water has donated a hydrogen to the acetate ion to equal to acetic acid. Step 4 is to put the second ice table and to put the information now that we know. So we know that our acetate ion has a mole of 0.05 for the initial, and it loses, for the change, it loses 1x. So our equilibrium would be 0.05 minus 1x. And we also know that the initial values of the acetic acid and the hydroxide are 0. We will need to find our Kb value. So to find our Kb value, we know our Kw and our Ka. We can find our Ka value at the end of our textbook, and the Kw value is a constant, which is 1 times 10 to the power of negative 14. So over here on your screen at the bottom right, we calculated our Kb value by dividing the Kw over Ka. And we can use that with our, as you can see at your corner left, we can use that to find the hydroxide solution concentration. Step 5 is to use the 500 rule. So we know that our smallest initial concentration would be 0.05 moles per liter over the Kb value, which we found out in our last slide, which is 5.6 times 10 to the power of negative 10. So if we put that into our equation that we figured out, we have 5.6 times 10 to the power of negative 10 equals x squared over 0.05. And then when we multiply the 5.6 times 10 to the power of negative 10 by 0.05, it gives us 2.8 times 10 to the power of negative 11, which equals x squared. And we take the square root of both sides, we get that x equals 5.3 times 10 to the power of negative 6. And this gives us our concentration of the hydroxide ions. Our last step is to find the pH and pOH values if the question tells us to. So our pOH value is like negative log of our concentration of hydroxide, which we figured out that is 5.3 times 10 to the power of negative 6. We put that into our calculator and we get approximately 5.38. And pH equals to 14 minus pOH, which we already know that. So we subtract 5.38 from 14 and we get 8.72. The pH of the solution increased as the base was added, which was important to know. This concludes the tutorial about how to solve a buffer system using a weak acid and a strong base at equivalence point.